Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're doing a practice problem on calorimetry. So go ahead and pause the video, work on this problem, and then when you're done, unpause the video, and I'll be working out the problem to give you the answer. So after analyzing this prompt, you're going to know that you're going to have to figure out the enthalpy change both theoretically and experimentally. We figured it out theoretically using the appendix in our book and looking up some values. We figure out the enthalpy change experimentally by doing calorimetry. So if you went into your textbook and looked up each of the values for our reactants and our products, the values that you should have got, okay, is the one that I gave you because it wasn't listed in our book of 100.5 or negative 100.5. The hydrochloric acid was negative 167.2, the silver chloride negative 127, and the nitric acid here negative 206.6 kilojoules for every mole. Now there's 1 mole, so it's going to be these numbers, and what you're going to do is you're going to sum up the reactants, and the sum of the reactants is negative 267.7 kilojoules. You're going to sum up the products, and the products sum up to negative 333.6 kilojoules. And whenever we do the enthalpy change theoretically, it's always the products minus the reactants or final minus initial for any type of delta. And if you work this out, negative 333.6 minus a negative 267.7 will give you an answer of negative 65.9 kilojoules for every mole according to this chemical reaction. So it's per 1 mole of silver nitrate, or per 1 mole of hydrochloric acid, or per 1 mole of silver chloride, or per 1 mole of nitric acid. You should get this amount of enthalpy change, negative 65.9. Now, to figure this out experimentally, okay, we're going to do the calorimetry. We're going to take the 50 milliliters of each item and we're going to pour it into a coffee cup calorimeter, and a chemical reaction is going to take place. I'm noticing that the initial temperature was 22.3 and it's increasing to 23.8. So we know that the heat is going out of the chemical reaction and into the water or the solution. Okay, so what we're going to do is we're going to figure out the heat flow going into the solution. Okay, the mass of this is going to be 100 because 50 and 50 milliliters together is 100 milliliters. The density is around 1 gram per milliliter. So if I have 100 milliliters in here and the density is 1 gram per 1 milliliter, then I'm going to have 100 grams for my mass. Remember, this equation is going to be mass times specific heat times delta T, or MC delta T. The mass being 100 grams. The specific heat of water and the solution are about the same. We're going to say it's 4.184 joules per gram degree Celsius. This is a number that you should have memorized. And then the change in temperature, we got to take 23.11 and subtract 22.30. Remember, final minus initial for any type of delta. And if you do that, you'll get 0.81 degrees Celsius. So if you multiply these three numbers together, you're going to calculate the heat flowing into the solution. Okay, so I get the answer of 338.9 joules. Okay, well, if this is how much heat is going into the solution, where is that heat coming from? Well, it's coming from the chemical reaction. So the heat flow of the chemical reaction is going to be the same magnitude as the heat flow going into the solution, but opposite in sign. So I'm going to end up getting a negative 338.9 joules. Okay, now I want the enthalpy change, and this enthalpy change is on a per mole basis. Well, I don't have a full mole of silver nitrate or a full mole of hydrochloric acid. So I'm going to have to use the molarity equation, which is equal to, molarity is equal to moles over volume. I'm going to do some cross multiplication so that moles is equal to molarity times volume. The molarity being 0.1, and that's moles per liter. and or big M, and the volume has to be in liters. So I got to divide by 1,000, so that's going to be 0.05 liters, and if I work this out, that's going to end up being 0.0050 moles. So as you can see, I'm only getting part of this heat, okay, because I only have a portion of a mole. So we want to get this value on a per mole basis. So we got to take this guy right here, the amount of moles, for the amount of heat that we have, and if we divide it, we will get it on a per mole basis. So take negative 338.9 and divide it by 0.0050 moles, and you're going to get this number of negative 67,781 joules per mole of the chemical reaction. Of course, this is in kilojoules, so we got to divide by 1,000 so that we can compare apples to apples, and that comes out to 3 sig figs. We'll round it to negative 67.8, and that's going to be kilojoules per mole of our chemical reaction. So I'm going to go ahead and put that answer in right here, negative 67.8 kilojoules per mole of chemical reaction. And you can see that these values are fairly close. Okay. Now, if we wanted to go a step further and calculate our percent error in our chemistry experiment, remember, you're always going to subtract these two and then divide by the theoretical value. So it's going to look something like this. In absolute values, negative 65.9 minus, I'm going to put that in parentheses, minus negative 67.8, okay, divided by the theoretical value, negative 65.9, times 100, and this will calculate our percent error. So let's go ahead and just do that in the calculator. So I'm off by about 1.9, okay, but when I divide it by the theoretical value and then times 100, I find that my error is going to be 2.88%. Not bad for a chemical experiment. So I hope you found this information helpful. If you like this content, or if this content helps you, please give it a like and subscribe. Adding a comment always pushes this algorithm to other students that are interested in learning chemistry.